All right, my plan today is we're going to start chapter 9, talking about chapter 9. So chapter 9, 10, and 11 are all like introductory calculus chapters. So this is likely going to be brand new for everybody in here. So lock in. I'm gonna present this to you in the simplest way possible to give you a little bit of intuition about like what it is exactly we're doing, and then like how to do it. So what I want to talk about for starters is just the idea of an average rate of change. So like so if you go 100 miles in 2 hours, what is your average rate of change? $50 miles per hour, right? Now, on that trip where you went 100 miles in 2 hours, were you going 50 miles an hour the entire time? No, right? You probably had to like back out of your driveway. You drove on some neighborhood streets that were probably like 25 miles per hour. You got out onto the, like a surface road. Maybe now you're going 40 or 50. You get onto the freeway. Now you're going like 70 or 80. You get back off the freeway and you slow back down again. So during this process, you may have only been at 50 miles an hour only a couple of seconds, right? Every other time you're either going faster or slower. Is everybody okay with this idea? So what if we have, say, the function, let's say y equals x squared plus 2x plus 3 on the interval (0 to 3). So what are we going to be doing here? What is this going to mean? If we abstract this now, instead of having like a distance and a time, you're given like a function and a interval. Well, this is kind of like our time. And this guy is kind of like our distance. So we're going to do this the same way. We're going to want to take like the change in y divided by the change in x. So if I plug 3 in, I'm going to have 9 plus 6 plus 3, which is 18. If I plug 0 in, that's 3. Right? Yeah, very similar. That's the piece that we should be looking at. What does this look like? Looks like a slope formula, right? So if we think about this graphically, you know, we have our parabola coming through like this, and we have like 0 to 3, and we're looking at that is like our slope, right? It's like the straight line. Now, is our function actually following that slope? Not exactly, but it's like the average rate of change for the function over that time period, or that interval. Does that feel okay so far? Now, that's lovely, right? But what we're going to be interested in here is not the average rate of change, but the instantaneous rate of change. So like that's going to be how fast you're going at some specific instant, right? Not what's your average speed over an entire trip, but at, 22 minutes and 52 seconds after departure, how fast are you going? Is the information that we have up here going to be sufficient to get that? Doesn't seem like it. If I want to know the instantaneous rate of change for my function at x equals 2, do I have enough information to get that? Well, if we follow the same idea that we did above, this would kind of be like that, right? If it's at the exact same instant, what's this going to come out to? No. Kind of. Worse than undefined, though. This is called indeterminate. When you have like 0 over 0. Different than like 5 over 0, which is undefined. 0 over 0 means that like literally you could assign any value to this, and we could make it a problem where like that's the value you get. Just to kind of show you as an aside here. Say like I have 5 times x minus 1 over x minus 1. If I plug 1 in, I'm going to get 0 over 0, right? Everybody agree? But if I just reduce this, that's going to be 5. So 0 over 0 could equal 5. And I could do this for like any constant out front and show that 0 over 0 could be any value, right? That's what we mean by indeterminate. Like literally you could assign any number to that. So that's not super. But let's think back to what we were doing, right? When we drew the picture. And we want this point 2, and then I guess the y coordinate on that would be 4 plus 4 plus 3, so 7. Now, if we go from 0 our average rate of change would be that, right? If we get a little bit closer, say we go from 1, 5, or if we get even a little closer, we do like 1.5 something. Did I do that arithmetic right? Oh, that's dumb. I picked a terrible example problem. Those aren't supposed to turn out to be the same numbers. But that's the idea, right? Is that what we're going to do is we're going to take like some x that's like getting closer and closer and closer to the value. And what we're going to do is we're going to say, okay, what happens as that increment goes to 0? So for example, again, if we want our instantaneous rate of change for, let me pick something that's less dumb. So let's just say we want to look at the instantaneous rate of change for x squared minus 1 at x equals 0. So what we'll do is we'll just start at, say, h equals 1, and then we'll just keep getting closer and closer and kind of see what's going to happen here. So we'd be doing, let's put an f of x in here. So I'd have like f of 0 plus 1 minus f of 0 over 1 minus 0. So that's going to be 0 plus 1 over 1, 1. So that's going to be negative 0.75 minus 1 negative 1 over 0.5.
Luca's dance here now.
Okay, Luca, I guess it's time for you to go. You too. So that's going to come out to be 0.5. If I keep on going, I think it's time to employ the calculator here. So there I'm going to get 0.25. Notice that as I'm getting closer and closer, let's see what's happening. Does it feel like that's going to be settling down to a specific value? What do you think is going to be happening as h approaches 0? Yeah, what do you think that instantaneous rate of change is going to turn into? Where does it look like these numbers are heading towards? Looks like they're heading towards 0. So the h is going to be what's changing each time. And the x is the 0, because that's what we're looking for the instantaneous rate of change was. So our function f of x is x squared minus 1. So when I'm plugging in 0 plus 1, it's just going to be 1 squared minus 1. That's where I got the 0 from. And then I have 0 squared minus 1, so minus a negative, that's where the plus 1 is coming from. Yep. I tried to pick numbers where it was going to be easy to do it in our head. So if we look kind of what's happening graphically, so this was our first instantaneous rate of change. That was our second. That was like our third. And here's what's the takeaway. Is the slope of this line that is tangent to f of x at x equals 0, that's going to give us the same thing as our instantaneous rate of change. That's what we're trying, that's what we kind of worked towards. Okay. Now, this is also going to equal something called the derivative of f of x at x equals 0. So when we talk about a derivative, we have a bunch of notations that we can use to represent this. So if I write d dx of, that means take the derivative of this function. And if I put a bar at the end, it will mean, and like a value for x, at that specific value. If we write dy dx, this is the derivative of y with respect to x. We could write it as y prime. This is the derivative of y. You could write f prime of x. This is the derivative of x with respect to, derivative of f with respect to x. So some important quantities and their derivatives. So if we have position, usually we represent that with the letter S. and we take the derivative of that position function with respect to time, we're going to get velocity. Usually represent that with v. So we might write that s prime of t is equal to v of t. Or you might write ds dt is equal to v of t. Just trying to practice using some notation, introduce you to some of these quantity relationships. If I then take the derivative of velocity with respect to time, guess what we get? Acceleration. Usually we represent that with like an A. So we could say that the second derivative of position is acceleration. Or you could say that the second derivative of position is the first derivative of velocity, which is acceleration. Or you could say like d squared s dt squared is a of t. Or you could say d squared s dt squared is equal to dv dt, which is a of t. Again, I'm just kind of trying to just familiarize us with some symbols and some notation right now. I'm not talking about how to do anything yet. So the how is still kind of a mystery, other than like building a table and doing the things like we've done. I'm just trying to like get used to some symbols. There's another quantity. The derivative of acceleration is called jerk. Again, we usually use a J. So you might, it's named after you, in case you're wondering. So we could say the third derivative of position is jerk, or you could say the third derivative of position is the second derivative of velocity, or you could say the third derivative of position is the second derivative of velocity, which is the first derivative of acceleration, which is jerk. Or you could say like d cubed s dt cubed is jerk. Or you could say again like d cubed d s, or sorry, d cubed s dt cubed is like dA, let's say d squared v dt squared, which is dA dt, which is just jerk. So again, I'm just kind of like showing you equivalent expressions, ways to write these things. Another common set of quantities that are related are like volume, area, and like length. Nah, let's not. I don't think that's going to come up. I lied. Let's not do that. So let's look at a little example here to practice using some of this notation. So it says a ball is thrown upwards from the roof of a building. The vertical height of the ball from the ground in meters after t seconds is given by the position h of t equals negative 4.9 t squared plus 18t plus 50. We're told the derivative of the function h prime of t is negative 9.8t plus 18. We're asked to find the initial velocity of the ball. So I remember that velocity is the first derivative of position, right? So in this case, velocity is going to be the derivative of our height function. And when we say initial, what time t is initial representing? 0. So what we want is h prime of 0. So if I plug that in, I get 18, and then if it's meters and seconds, this should be meters per second. Joey. So from before, we said velocity is the first derivative of position, right? That's what we said right here. So that's just me writing that down, that I knew that. In our case, our position function is what we're given. Well, they told it to me. It says the vertical height of the ball from the ground. That's describing a position, right? That's where the thing is located in space, right? That's a position function. Does that feel good? Okay. We're good then? Okay. It says find the time at which the velocity of the ball is 0. Interpret interpret the meaning of this. So I want to take v of t equal to 0. And I remember v of t is h of t, or h prime of t, excuse me. So that's negative 9.8t plus 18 equal to 0. So t is going to equal negative 18 divided by negative 9.8. So about 1.84 seconds. Who can tell me the meaning of this time? No.
Oh, wait. Is it the air? Is it stops?
Yeah. So if we wanted to like draw a picture of what's going on, when we throw our ball up in the air, that's kind of the path of the ball, right? At the very apex of that ball's path, at time 1.84 seconds, that ball is going 0 velocity because it's slowing down as it gets to the apex, stops for just an instant, and then starts speeding up back down towards the ground, right? Joey?
V, T, that's the velocity.
Correct.
And then H is the
H of t is our position function. Yep. So h prime of t is our velocity function.
H prime of T is the velocity.
Because velocity is the first derivative of position. And then it says find the velocity of the ball the moment it hits the ground. So to do this, I need a time, right? I need to know what time the ball hits the ground. If we're talking about the ball hitting the ground, are we talking about position or velocity? Position. So I need to find when h of t is equal to 0, and I'm going to use that answer for t to plug into v of t to find that velocity. Is everybody okay with that idea? Correct. If a height 0, if the h is the distance the ball is from the ground, height of 0 will represent ball on the ground. Everybody feel good there? So how should I solve this equation? I would use the quadratic formula, absolutely. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, what kind of answers are going to be feasible or infeasible for time? What kind of time answer is a nonsense answer? Negative. So if I get a negative answer for one of these two, I should be getting two solutions, right? Or possibly two. That's going to be an indicator to me that that's not the one I want. So there I go. I got a negative. That's not what I want. So I'll just go back and change this from the plus to the minus, and we'll find that answer. There we go. So we got negative 1.85 and negative 5 or positive 552. Yep, and those are in seconds. So now what I'm going to do, I'm going to do v of that number, or really h prime, because we know that those are the same thing in this problem, of that. So I have negative 9.8 times my answer plus 18. So I get negative 36.11. Now, is it okay for velocities to be negative? Yes. What does a negative velocity indicate? So it's, in this case, which direction is the ball moving? Towards the ground, right? Which should make sense, because as it's hitting the ground, it's heading down towards it. So the instant before it hits the ground, it's going 36.1 meters per second toward the ground. Yes?
So, why did you just do you got the same time?
Yeah, so the question asked, find the velocity of the ball at the moment it hits the ground. So the first thing I had to do is find the moment, and then once I had that, I can plug it in for velocity. We'll do some more on this next time.
I just remember, like, what is equal to what? Like,
Yep.
Is that
No, don't you don't have to memorize anything right now other than like position, velocity, acceleration. Like the derivative order would be the only thing to be memorized here. Because we still have yet to show you how to find these derivatives.
yeah.
That's still coming.
Okay.